Hello, good morning, good afternoon, and good evening, wherever you are. And welcome to the Synchronization and Timing Self-Paced Bootcamp. My name's Dennis Haggerty. I work for Cisco Systems, and I'm part of the Service Provider Access Group, which deploys devices at the edge of the network for service providers, the people that give you, sort of network services. And what this is a three-part bootcamp explaining the introduction, an overview if you like, to synchronization and timing. The previous two parts, which you'll also find on the YouTube channel, part one explains really the concepts behind timing and synchronization. It gives you an introduction to frequency-based timing. It talks about how we do it, why we do it, who wants to do it. It tells how we measure the quality of it. It starts to introduce the concept of time and phase synchronization. And then part two, we really dive into phase and time synchronization, specifically packet-based with IEEE 1588 and PTP. We talk about the protocol. We talk about external timing interfaces and how we do phase synchronization with them. We discuss PTP profiles and standards, and also some considerations for deployment. And this is part three. So part three is synchronization and timing configuration. So what we really want to cover here is, so we understand the concepts of synchronization and timing, we understand phase, and we understand time synchronization. We now know what PTP looks like. The idea is, now what do I do? So what I decided to do is to pull together a presentation which gives you an example of configuring PTP on our SPAG products. So what we'll do first, we'll go through the supported and unsupported features, which we touched on in part two. Then we'll look at configuring the global sync options, so things that you require before you even start configuring the specific sync requirements. Then we'll look in turn of how to configure TDM sync, how to configure synchronous Ethernet for frequency sync, how do we configure PTP, and we'll cover slave clock, we'll cover hybrid clocks, we'll cover master clocks, we'll cover boundary clocks, we'll cover hybrid boundary clocks, even transparent clocks. So the idea is that you can come to this presentation and it will give you an idea of how to configure it for each of the platforms. So the way it's structured is like this. We've taken four basic platforms from our organization. The first one is a ASR 901, which is like an entry-level router typically deployed for cell sites, so in the base of cell sites. Then we have an ASR 903, which is a pre-aggregation router has the current switch module is called an RSP1. There's a new RSP2 coming, and the features will be pretty much in line with it very soon now. So I think the first release mightn't be 100% compatible, but certainly by the next release the idea is to have full compatibility. But anyway, this will cover the RSP1, give you a very good start with RSP2. Also the little brother, the ASR 902, is the same switch modules as the 903, uses the same switch module, same RSP, but it just only has one rather than two, so it doesn't have redundancy. So wherever you see our ASR 903 mentioned here, we're also talking about the 902. Also we have the ME36 and 3800, which are carrier Ethernet switches, and we're only going to cover them partially, I say, and the reason is because really they don't fully support PTP. They also don't have any TDM interfaces, so they don't have requirements for things like phase synchronization or for physical input and output of time of day and 1 pulse per second. But I'll cover them for things like SyncE. And then we have the same carrier Ethernet family, but there's a special version called the 24CX, which does have TDM interfaces and does have inputs and outputs for phase and time of day. And through this presentation, rather than call it constantly the ME3600-24CX, I'll just call it the 24CX. I won't talk about the 9K. I also won't talk about the 7600 or legacy products like the MWR, although I will refer to some slight differences where they turn up. Say a little over an hour in length. Famous last words. The first one of these sessions I thought would be an hour and a half, and it was 2 1/4. The second one I thought might be a bit over an hour, and it turned out to be nearly 2. But anyway, I have a hard stop for recording this in about an hour and a quarter, so it cannot go too much longer. Now, there is a lot of information here. We really don't cover the concepts very much. More what we're covering here is the configuration. So you should understand the concepts, and now we're telling you how to turn each particular concept on or turn a particular feature off. And I don't expect you to try and remember this. The idea is for reference. I will go through it to explain the highlights of each platform and each feature we're configuring. I will not go through it line by line. We'll be here for ages, and I don't think it's valuable. Really, what this is for is if you need to configure, you need to put together a proof of concept. If you need to do some testing, you can take this presentation, you can find the platform you're interested in, and you can pretty much cut and paste. What I also cover, and what is probably the most valuable part of this, is that if there's any differences in platforms or if there's any little tricks that I've discovered, I've captured them all in this presentation. So from my point of view, this is probably the most complete and up-to-date capture of how to configure these platforms, either together or multiples of them in one place. And the way the structure is, for each feature I go through each product in order. So I've introduced the feature, then I have the ASR 901, then the ASR 903, then the ME series. So just be aware when you go to a feature, the first slide is probably talking about the 901 and the last one is about the ME series. So pick your feature, pick your platform, and you should be good to go. The other way it's been designed is that you can come along and you can pull particular features out and put them together. So if you need TDM input, you go to the TDM input section. If you need SyncE output, then you can use the SyncE output section. If you need PTP input, you figure out the PTP slave is what you require for input, and then TDM output. So you depending on your input and your output, you pick the section you need. And with that, we'll get started. So supported, unsupported features, just sort of highlighting some of the differences here. In general, across the platforms, they're pretty similar. The only differences really are, as I said, about the 3600 switches. Carrier Ethernet switches. For the synchronous Ethernet support, they only support SyncE input on the NNI ports and support SyncE output on the UNI port. So you can't take synchronous Ethernet in on a UNI port. And given the market they were designed for, that's a fairly common trade-off that's made. The new version of the ME36, the 24CX, the one we're talking about, that's not true. So this is only for the classic non-TDM 3600s and 3800. The 901, 903, no problem on the 24CX as well. For adaptive clock recovery, generally not supported. The reason is it's fairly limited what it can provide. I didn't really describe exactly how it works because really very few people are using it anymore. It's really a point-to-point solution. If you have like one E1 coming from one site going to another, then you could use adaptive clock recovery. But for most environments, you're using more than that, so it's not relevant. Ordinary slave, master and boundary clock is supported across all the platforms. Of course, as I said, the 3600 classic carrier Ethernet switches, there's no hardware support for a PTP in there, so they don't support it, and really it's not required on that platform. The only reason you would use it is to transport PTP packets and to switch them, but it doesn't get involved in PTP processing. TDM line clocking, the 24CX has got TDM ports, the 3600 and 38 do not, so it makes no sense for it to be supported there. 901, 903 of course support line clocking. Best master clock algorithm, We support that across all the platforms. The 901 also supports 8265.1 alternate best master clock algorithm. I'll explain a bit more about that later. We support that alternate best master clock algorithm actually in all those platforms. But really we're talking about redundancy. The 901's redundancy is through the alternate best master clock algorithm, and the other platforms support both sets of redundancy. Transparent clock supported not in the 901. Really there's hardware limitations there as to why it's not supported. It's supported in everything else. And I think going forward it's fairly clear to say that all our platforms will support transparent clock. Hybrid clocks now supported on everything. Boundary clock supported on everything. Telecom profiles supported on everything. VRF aware PTP is supported on everything. And what I mean by that is that you can put your PTP interface, if you like, you can put it into a VRF and keep it out of the global routing table. PTP over Ethernet becoming more common. It originally was deployed in industrial applications. Now it's becoming more of interest to telecom providers in some circumstances. Some cell site devices support PTP over Ethernet. So it's supported on the 903 unicast, 901 multicast. There's reasons for that. The 24CX doesn't currently support it. We're still working on that. And the configuration of delay asymmetry, what that means is that where you have asymmetry in the return path between the forward path and the return path of PTP, if you have asymmetry you can get phase offsets which are not reflecting. You need to correct for them, and the way to do that is you can measure it externally and update a field in the servo on the PTP slave and account for that phase shift. That feature is coming in the 901. We're still working on it for the 903, and it's a bit further out for the 24CX. So the 901 makes more sense because that's normally connected out at the edge, right at the edge of the network. So that tends to be the last slave in the chain, and so that's where it's most important. So just to give you an idea of the end-to-end features that we support. As I said, most of the platforms very similar support. The only differences are really where the hardware, it makes no sense to support it. Now we look at the global configuration options. So now we're going to start talking about the CLI and actually how we configure these platforms. But first we'll cover a couple of little items that we touched on in part one, because we're going to configure some portions of these now. The first one was holdover. What this diagram was used was to show that we have a clock source here, which we have defined as a clock source to our router. This is our system clock from our router here. And what we're showing here is that we have a clock source which goes along, and at this point here we lose the clock source. So our clock is synchronized in orange here to input A, and at this point it no longer has clock source A. There is no clock source B. So we go into what's called holdover. And what this means is that our internal clock was recently synchronized to an input, to a frequency source, and is now running based on its own oscillator. But the difference here is that the oscillator has been conditioned, and is being adjusted using data acquired while it's been synchronized to another clock. So it's better than having no source at all, but over time, of course, it tends to lose its accuracy just because it hasn't been synchronized to a source for quite a while. And at some point, it comes back, and we then connect back to using that as a frequency source. And that's what we call as well revertive mode, which I'll cover in a sec, where we revert back to the source that we originally had. Here you can see where we have it with clock source A and clock source B. Here where we have clock source A, we go to a clock source B, and then when clock source A comes back, because we have configured revertive mode, we actually no longer use the B source. We revert back to using our primary source A when it becomes available. Switch back to the best clock, or more accurate to say, to the primary clock we've defined when it is available. Two more things we need to define. There's what's called a hold-off timer, and this is really just to keep the sets, which is the device, the timing system, within the device that keeps track of the time for you. Generally just pieces of hardware, and generically known as sets, and I'll sort of refer to it as sets throughout this presentation. And for stability, you don't want inputs coming, being intermittent on and off, or coming back and then disappearing again. So you define a hold-off timer. The hold-off timer really dampens short interruptions. So what you do is you don't really switch away from something until it disappears for a period of time. So short oscillations, you stay where you are. It's only when you see an extended outage that you can then switch to your backup source. And then the next piece is a wait to restore timer. The wait to restore timer means that when your source comes back, before you switch back to it, because it might have some latent instability or might be some issue with it, you actually wait a period of time before you actually switch back to your primary source. And the reason I touch those is because we're going to configure them. The last piece, sort of non-graphical, is what I covered in part 2, which is the QL enabled mode and the QL disabled mode. And this is G781, and it's defined in the standard to basically select your clock based on the quality level of the clock. So you have two ways of doing this. You have it where you do use the quality level, or you have it where you do not use the quality level. So that so if you have two clocks available and you're in QL disabled mode, you take your priority. As long as they're not failed, then you take the priority, the one with the highest priority. In the QL enabled mode, it doesn't matter what the priority is. If the quality level of your secondary clock is higher than your primary clock, you will switch to use the secondary clock. So the actual quality is the feature that is used to decide the clock input more than the priority. So it will take a lower priority clock with a higher quality level when you have QL enabled mode. Obviously that's a fairly good thing to do. So now we've covered those concepts, we define them. So this is fairly standard CLI, Cisco iOS, not a trademark of Apple, definition of CLI. And what this allows us to do is to now define the global options which we've just discussed. So first of all, and this is fairly standard what we would define on every network element. The first thing is to say we want to have network clock synchronization automatic. And what this means is that we're going to turn on G781, and you definitely want this turned on. And then the second thing we're going to define is that we need QL enabled mode. As we just saw, again, probably a good thing. You want to take the best clock that you have available. And then the wait to restore timer, generally the default is 300 seconds. And then there's a hold off timer, which we said is that for the small intermittent blips in your input signal, how long you wait before you hold on to that before you actually go back to another signal. And we have revertive, which means when you come back from a backup clock, you go back to your primary defined clock, of course as the highest priority and at the appropriate quality level. So generally you want defined like that. There's no really any reason to change them. The one exception is the wait to restore timer. The wait to restore timer is 300 seconds by default, and if you're testing, going forward and back between holdover and clocks coming on, clocks going off, quality levels changing, you don't want to wait 5 minutes for the node to react every time something changes. So normally for testing you set that down to 5 or 10 or 15 seconds, so that when you change the quality level of an input clock, or you take an interface to a reference down and it changes clock, it does it within a few seconds and you don't have to wait 5 minutes for it. So I've actually had calls from people who have been doing testing and can't understand why they changed something and nothing happened, and the reason is because of the wait to restore timer hadn't gone off. The next thing we need to define is a SSM option, and really this just tells what part of the world you're in. Option 1 is the ITU world, and in the ITU world you talk SDH, you talk E1, and so you select option 1. If you're in the North American US type part of the world and talking ANSI and Sonnet, then you'd be option 2. And then you start talking about TDM interfaces being T1 circuits rather than the other part, which is E1, which is the non-US European part of the world. There is actually option 3, which is Japanese standards. Most of these platforms don't really support option 3. We'll point out we're talking about holdover mode. What used to happen in previous CLI that we had some years ago on older platforms like the MWR, you could actually define how long you wanted to stay in holdover before you went back to free running. So this is where you basically said, look, my clock has been conditioned from a source, but it's been a long while, and so I think really it's probably no chance trying to still maintain that I still have some form of accurate clock, so we'll just give up and say we go back to just free running off the internal oscillator, and you used to be able to define that period of time. There's no equivalent CLI for that, probably for the good reason that trying to define the proper value for that was almost impossible, because it depended on a lot of things like how old the equipment was and what temperature it was and everything. So that concept has gone, and there's no CLI for it. So generally these things will stay in holdover for 24 hours and then revert to free running. So they're the global options. So before we configure anything else, we would probably cut and paste those fields into the configuration, global configuration CLI on the iOS switch. Now we're going to talk about physical frequency sync using physical frequency inputs. So what are our options here? I show on the top right hand corner the interface front faceplate on the switch module for ASR 902, 903. We have a bits input, which is probably the most common. Most of the platforms have a bits input, and so we can take bits input of various flavors, E1, T1, 2 megahertz signals. We can also take TDM in, so if you just have an ordinary E1 or a T1 TDM circuit on your board, then you can take frequency in from that. You can take it in from Synchronous Ethernet. Show a picture there of a SFP cage. But 1 gig E, 10 gig E, you can take in Synchronous Ethernet. Also, there's ways of taking it from GPS receivers, like a 10 megahertz signal, which again has a plug on the interface here for output from a GPS receiver. And I said, as well as the E1, T1 ports, that you also have optical ports like Sonnet and SDH, which can give you frequency reference. Here I show it for bits ports. We show the bits ports on the various platforms. I've also included the 9K as well, on its RSP 440 has bits ports, and it also has GPS ports as well if you need those. But at the moment we're just talking about Synchronous Ethernet and using bits as a reference, as a frequency reference. So I'll go through the highlights of each of these a little bit slowly, and then as time goes on you'll start to see they're a bit repetitive, so I'll leave them there for reference, and we won't, as I said, go into each line by line. So a couple of these, the first item here is generic really, as well as being able to set the generic option for SSM. Normally what we do here, we set this network clock synchronization SSM, as I said, so, and that says whether you're using an E1 or a T1 rate. So really before you start and you want to get T1 CLI, you need to do that on the bits port. So if you receive a router and there's a bits port on it and you can't configure it to T1, or there's no T1 CLI, it's because you haven't set this value here. So it's very important to set that right up front, as I said, in the global options. Once you do that, then you pretty much will be talking E1. And then I go through each of the platforms. So the 901, the 903 on this page, the MEs are on the next page. And you can configure then network clock input source. So this is basically saying to the network clock process, look, we're going to have an input frequency source here. You can give it a priority, just a number between 1 and 250, 255. So normally, say 10, and then you put the name of the bits port. And really, this is the only slightly tricky bit. That on a 901 it's called external 000, and that means bits port. Then if you've turned on, if SSM1 is on, which is the default, you'll be able to put in E1. If you cannot put E1 in there, it's because you have configured option 1. If you want to see the CLI, you need to have option 2. So that's what I was explaining. You need to get the SSM right before you start. And then you can configure things like the options to E1, whether you use CRC4, what line coding you use, and so forth. We explained before about SSM. If you're going to use the clock quality from SSN, then you need to be sure that you use CRC4 and ESF on the T1. Otherwise, you're going to have a problem. If you want to use a 2048 signal, so rather than an E1 digital signal, you're using a wave signal, then what you do is you define it as 2048 rather than E1. So there's your options: E1, T1, and 2 megahertz. Pretty similar on the ASR 903. On the 903 though, instead of calling it an external 00, we call it R0 or R1. And the reason for this is because we have two inputs. On the 903 we have two route switch processors, two RSPs, and what this means is that you can define the inputs on one RSP or the other or both. So this allows you R0 being the RSP in slot 0 and R1 being the RSP in slot 1. Similarly, you can define your line codes, same with the T1, and then also if you require 2048. I also will point out that if you want to have a different hold-off timer for a bits port, you can also configure a hold-off timer for that specific interface. So we had a global hold-off timer, but you're able to define that hold-off timer on a specific interface as well if you require a different value for it. Going to the ME series switch, I put this in for like the third time. If you want to see the T1 CLI, you need to SSM bits properly. And again, with network clock input priority, I said no, say 10. The other slight change here is that the bits port on ME series switches is known as external 100. So it's external 000 on the 901. It's R0 or R1 on the 903 or 902. It's R0, and then on this one it is external 100. But again, the same CLI. It's really the only slight wrinkle is the name of the port. On the 7600, there was a configuration option to do with controller bits. So rather than talk about external 111 or R0s or R1s, it had a controller bits. You would configure the controller bits. In some earlier versions of iOS XE, that CLI is still there. However, it's not functional. So if you're used to the 7600 defining controller bits, yeah, the CLI might be there, apologies, but it's actually non-functional. You have to do it through this new network clock CLI. So now we've seen how to configure bits as input. What happens if we have our frequency source from somewhere else, like from SyncE or PTP or something, and we need to give bits output to something else? This is supported again across all the platforms, and it's very similar to the input. Really, the only change is instead of input source, you're now talking an output source. So what this is saying is take the system clock, which is the output source is the system, and make it available at this priority again. Just give it a number 10, and where do you want to push the signal? And on the 901, external 000 is is the bits port on the 901. Again, depending on what the downstream system needs, you might define the CRC and values and the framing and so forth. Same with T1. Again, be sure the SSM set right, and also a 2 megahertz signal. On the 903, same again. Here we have R0 or R1 on the 903. The 902 only has one R0, so the R1 doesn't make sense there, but R0, R1. And the bits port on the ME series switch, similarly, this is external 100. So means output source is the system clock. We've recovered our clock quality from somewhere else, and we're going to put a bit signal out of our bits interface. So one question people might ask is, why do we put it out the bits interface and not out of the E1T1 port, like if we have an E1T1 port on the 901 or the 903? And the normal answer is that SSM might not be supported on the E1T1. So if you need to give SSM bits down to the downstream system so it knows the clock quality it's getting, you have to use the bits port. Now we've done the bits. Now we look at a normal TDM port. So if we have, the 901 has up to 16, depends on the version. It has up to 16 ports. There's some that don't have any, but just so you know, the 901 does have models that have T1E1 ports up to 16. Some of them may be port-based licensing, so if you need another one and you only can see 4 or something, you might need to install a port license to get them all. Now, before we start to use TDM ports, you may be aware you need to define what the card type is. Again, this goes back to the old T1E1 ANSI ITU problem. So what you'll have to do is to define the card type, and then you put in the keyword either T1 or E1. And what that does is define the card type and loads it with the microcode to support that speed and that framing type. 00 on the 901 means all those 16 ports that are sitting there. So that will configure for T1 or E1 CLI from that point forward. Default is E1, so as it comes out of the box, which means you don't need to do anything for E1, but you can then go and say, okay, I am getting input clock from my E1 port 00. Again, as I said, the E1 port doesn't support SSM. The bits port does, so if you need SSM, you plug it into the bits port. If you cannot plug it into the bits port, unfortunately you have to work without SSM, or you can define an SSM value specifically. If you need T1, you need to set the card type to T1, and then you see controller T1. So what this will do is this will say, I'm going to get my clocking from port 00, and that'll be my input clock. Now, the difference on the 901, a slight wrinkle here, is there's no clock source CLI on the interface. Normally what you do with these platforms, well, you'll see in the next one, you configure the clock source line, but there's no clock source line on a 901. You have to use this to say, I'm taking clocking from that TDM interface. So we'll see slightly differently here on the 902, the 903. Similarly, we have to define the card type. Two things you really should do. You set the synchronization option 1. If you want E1, well, that's the default. If you need T1, you set option 2. Then you do card type. There's up to 6 modules in the 903. There's 4 modules in the 902. So you say card type E1 0, and then this number here says which slot that you wish to set the card type. So you can actually, if you wanted to, you could have T1s in one and E1s in the other. So once you do that, then you can configure them as either E1 or T1 ports. So this is the way that it used to happen on the 7600s and happens on all the other platforms. As I said, on the 901, this CLI does not exist. You need to use the input source command. But normally for TDM ports, what you need to do is to define a TDM as an input clock. You do clock source line, and this means take the frequency from the line rather than the internal oscillator. And so what you do here is you say the controller, in this case it's port number 3 in slot 4 and it's clock source line, and that means that that controller will then take that clocking, make it available to the internal oscillator. Then we have to add this thing to say take that clocking information from that controller and clock our internal, condition our internal oscillator, what's called T0, condition it based on that controller's frequency. So this will take this frequency from the line on this controller and it will make it an input source to our internal clock. Now for people that are used to configuring routers in the past, this is probably not new, but maybe the new piece here is this component here, because what we're doing now is we're actually taking this and making it available to the whole platform. So that line, what's plugged into 043, will become the frequency source for the whole platform. Similarly for T1, won't go through this in a lot of detail. Also we can use for Sonnet, it doesn't have to be E1, it can be an optical interface like Sonnet or SDH. The difference between Sonnet and SDH CLI is not much, you just put a different framing line in, but you do refer to it as controller Sonnet. Clock source line, and similarly you say control Sonnet, whichever port you want to use. You can use up to 4 TDM clock sources on a 903 with a maximum on any with a maximum of 2 on any interface module. And I will point out, if you're having a problem using the Sonnet port, it's because the ports on a Sonnet interface on a 902 and 903 require a license, a port license. The ME3600 24CX. So the 24CX has TDM ports, so it also has Sonnet SDH ports. So it's very similar to the other ones. You need to make sure your SSM is set correctly. You define your card type as E1 or T1. The difference here is that the TDM circuits on the 24CX are 01. And then you do very much the same. You take the port name that the interface is plugged into. You do clock source line, network clock input source, and again you just define the controller. Same for E1, same for T1, same for SDH, same for Sonnet. Similarly, there might be port licenses on a 24CX specifically for Sonnet. Again, we have the advantage, disadvantage. Of course, we could all use bits output off the 24CX, but we can use this as well. The disadvantage is that you don't have SSM support. So that's really only the slight downside, but of course you have up to 16 of them. So the other thing here too is the numbering on this might be slightly different, because the Sonnet ports start at 0, whereas the E1 start at 1. And the reason for this is long and complicated, but yeah, the numbering on the 24CX might be 1 out, it might be 1 based instead of 0 based, and that's a legacy of a carrier Ethernet background. So defining say we have a platform now that we have our internal oscillator is conditioned to something, whether it's bits or SyncE or PTP, and now we want to use our internal clock, which we've now got conditioned to something. Now we have a frequency source for it, and we want to use that to drive a TDM port. So we're not talking about bringing TDM in and driving our internal T0. We're talking about using our T0 to drive a TDM circuit. So we'll cover this other platforms first. So the 902, 903, 24CX, they use all very much the same CLI. So you just say controller and then you say clock source internal, and what that means is you use the internal oscillator to drive the clock for that circuit. So same for E1, same for T1, same for SDH, same for Sonnet. The only wrinkle, as I said, on the 901, there's no clock source CLI, so you can't put a clock source internal. And the good thing though is that the 901, the default is clock source internal. So there's no CLI, so on the 901 you don't need to configure anything. If you need to use the internal oscillator for a TDM circuit, the default is clock source internal, so there's no configuration required. The problem with the other platforms, why you need to do this, is that most other platforms, clock source line is the default. So generally all the 902, 903, 24CX, 7600 clock source line's the default. In this case, you'd have to configure clock source internal. The 901, there's no clock source internal. Clock source internal is the default. If you want to go the other way and you want to use the line as an input, then you need to use the network clock input source command, as we covered a few slides ago. Hope that's clear, but yeah, that's the only slight wrinkle in that area. So TDM, it's all fairly straightforward. What we'll cover now is synchronous Ethernet. We'll basically do the same thing. Synchronous Ethernet is input, synchronous Ethernet is output. So as I said, you can take this presentation, you can chop it into pieces. If you have SyncE input, TDM output, then you can pick which pieces you want to use. So you would use that second part that we just covered, and if you want to use input, you'll use the piece I'm just about to do now. I think a lot of people have experience with SyncE these days, so we won't spend too much time on it in the interests of keeping this short. A reminder of what SyncE is. It's a way of transferring frequency over a physical medium. As I said, there is no SyncE packets. There's no such thing as a SyncE packet. It's using the signal on the wire to be able to send frequency down the line. There are frames, there are packets sent for ESMC, but that's really above SyncE. SyncE is just using the actual signal on the wire to send frequency as well as data. If you have some questions on that, then you go and review part 1, where we cover synchronous Ethernet. A couple of things to start with. Again, there's some global configuration options, and there's some things that will never work and will work. The first thing is, on these platforms, the management port does not support SyncE, and that's pretty true of a lot of platforms. Is that there's a separate Ethernet management port, and it will not support synchronous Ethernet. We get asked this a lot. Copper SFP will never support SyncE. There's basically not enough pins in the actual SFP to be able to do it. Some people have tried there are some proprietary solutions where they can try and send it in one direction. There's all sorts of issues with them though, which we can. If you have some questions, you can probably Google the web to find the answer to that. But there is actually some very good reasons why it doesn't work properly, and it's all to do with the hardware support and the original Ethernet standards. You can also specify the flavor of EEC. This is Ethernet equipment clock. So what this does is just define which part of the world you want to work in for Ethernet, and it doesn't change the Ethernet as well. It's really an ESMC issue. So again, option 1, ITU, rest of the world. Option 2, ANSI, US, part of the world. So this is pretty much defining for G8262 what we defined for G781, which was the SSM option. Then the first thing we need to do after that is to turn on ESMC, and we just do that with a simple configuration command. It's got to be put in a configuration mode called ESMC process. And then once you've got your SyncE, you can configure clocking for output. You can take output for SyncE and you can generate it based on it being recovered from one of these inputs. You can take it in from SyncE, you can take it in from bits, you can take it in from TDM, you can take it in from slave, condition your local oscillator, and then you can put SyncE output based on your local oscillator. And that's what we'll go through now. So first of all, we'll just cover a couple of little ESMC things and other global values. So normally if you have an interface gigabit Ethernet 1 synchronous mode, that's sort of generally how you turn synchronous mode on most platforms. What you are able to do though is that when you turn on synchronous mode and you start to use it in the synchronous Ethernet, ESMC packets start flowing over it as well, and ESMC will determine from the other end what the quality of that clock at the other end is, and you're able to affect that. So we won't talk about it too much, but so you're able to change your ESMC mode to say I don't want to worry about quality levels. You're able to transmit or receive particular quality levels, so you can override them. And these are the ESMC values which you can send and receive. So there's option 1 ITU values, there's option 2 generation 1, option 2 generation 2. So just so you know, you can actually go, you can turn it off, or you can transmit or receive a number of quality levels. Of course, if you do that, you run the risk that if something changes and you've defined you have an interface that doesn't run ESMC at the other end, and the guy tells you, oh look, it's primary reference clock, so no problem, PRC, and you do that, and then all of a sudden it's not a PRC any longer, and you're still synced to it telling your node that it's a PRC and it's not, then it's a problem. So this is why ESMC is there, is to dynamically reflect the change in clock quality. Of course, said before, things like hold off values, wait to restore, you can modify them as well globally, but you can also do it on a per interface basis if you require. So SyncE is input, ASR 901 is the first platform. There's 3 basic sets of ports on the base 903 TDM version. There's copper ports, which is port 0 through 3, which are standard RJ45. There's combo ports, which are a mixture of RJ45 and SFP. And then there's optical only ports. And to get the best result, we find what you need to do, as well as going in and defining synchronous mode, you really need to go and define what mode it is. So if it's SyncE state slave, then you want to configure SyncE state slave, and that means you take your sync from the other end. What this basically means is that that you are doing clock source line. If you do that, that means that your internal oscillator then needs to be synchronized to that. So you define this network clock input source and say, yes, interface 00 is going to define my internal T0 oscillator. So slave means take the clocking from down the line from 00 and condition my internal oscillator to reflect it. Of course, that means all your other ports should be clock source internal or the equivalent, and what you do with synchronous Ethernet in the 901, the equivalent is to say SyncE state master. So that means anything you connect into it will give the frequency source down to the downstream systems. If you're on a combo port, you don't need the SyncE slave. It will negotiate it, but you really need to configure the media type. Auto select, you probably get better results by specifically defining which type it is. If you've plugged it into the RJ45 port, then you should plug it in. If it's in the SFP port, you should say media type SFP. Similarly, you have to define the network clock and say my interface is 04 is giving my internal synchronization to my internal oscillator. On the optical ports does this all automatically for you. So all you have to do is say, oh, this is a synchronous port. ESMC will handle it all for you. And then you do the network clock input source and say, yes, I want to use gigabit 0-8 as a possible solution to drive my internal oscillator. What I didn't quite mention is you can have multiple of these network clock input sources. So you might have connections to 2. So you can put a priority 10 on this one, and you can put a priority 20 on the next one. And what it will do is it will select the highest priority as long as the quality levels are the same. Remember, we talked about QoL levels. So if this is PRC, then it will select that one. If this one is not PRC, say it's like an SSUA, and this one is PRC, then if you use, get that right, bad writing, if you use QL enabled mode, then it will pick the PRC. If you don't use QL enabled, so it doesn't take account of the quality level, it will just use the highest priority. So generally, it pretty much handles it all for you through ESMC. On the 903, this is all fairly straightforward. What you do is you have some various options. So you have an RJ45 interface module. So there's an interface module on the 903, 902, which just has RJ45 copper ports on it. And you just define synchronous mode, network clock input source again, whatever the port number is. Remember we said if you have an SSP with a copper SFP, SyncE is not supported. Never will be. If you have an optical SFP, then what you can do is, again, you just configure synchronous mode. Normally what you should make sure is configured also is negotiation auto. You'll get better results doing that for complex reasons to do with 802.3. But similarly, then what you want to do is do a network clock input source. SyncE input on the 10 gig, so they have on the 902, 903, there's a 903 IM. It's actually not an SFP, it's an XFP, but there is a new version which contains 10 gig SFP plus SFP. So what you can do here is you have similarly, you just define the synchronous mode and then the network clock input source, whatever the name of the interface is. So that's all pretty straight. Similarly, you can have up to 4 SyncE clock sources with a maximum of 2 per interface module. The ME series switches. So we said before SyncE input is only supported on the NNI interfaces on the 36 and 3800. So the output will show in the next section. If you have the SFP, because there's an SFP based version and there's a RJ45 version of the 3600, but of course it doesn't make any difference. The input's not supported and certainly not supported on the copper SFP. If you have an optical SFP, again 36 3800, not supported for input, but the 24ACX does support it. So you can take in, like the 901, the 903, you can take in synchronous Ethernet on one of the gig E ports with optical SFP. And you just configure it, negotiation auto, synchronous mode. Again, it's nice for the combo ports if you define what the media type is. You get better results from doing that. With the 10 gig E port on the 36 and 3800 has XFP plus for various reasons. And the 10 gig E port, similarly, you just define synchronous mode and you say input source again, and you can get it from, you'll pick up the clocking from the 10 gig E interface. And from the 3600 actually has an XFP, really for extended environmental range support. Again, you just configure it as synchronous mode. So all fairly similar. Negotiation auto, media type if it's a combo port, synchronous mode. It's all fairly straightforward. So configuring PTP slave clocks. So what we've done now, or perhaps I should just cover here as well. When you're talking about configuring a SyncE as an output, here you have where you've got synchronous mode defined. That does both for you, because ESMC is going to control that. So where we say here gigabit Ethernet 0/1 synchronous mode, that's saying we're now participating in the SyncE network. This line here says, oh, and by the way, take that source in and make it available, if it's got the appropriate quality level, to be the source of my internal oscillator. But all the other ports you have defined with synchronous mode will actually be outputs. So that'll be output for SyncE. So as soon as you turn on synchronous mode on an Ethernet port, it will use it. If it has the quality, ESMC will organize it and say, yes, okay, this can output SyncE because I am getting my quality from a primary reference clock, so it will put it out that port. So I didn't really cover the SyncE as output here, and the reason is because it sort of all happens automatically. So next we'll talk about PTP. PTP as an input. So the oscillator is conditioned by PTP from from a remote master. So we'll cover this in a little bit of detail, and then the rest of them are all sort of similar copies of this. So first of all, we've got to define a loopback address, and this is fairly typical of how it's done on all these platforms. So you define a loopback address. You give it an IP address. Of course, loopback address has to be -32 mask. The only wrinkle on a 901, don't use VLAN 4093, otherwise you'll have issues. Normally, when you define the loopback address, before you define PTP on it, you want to ping it. That's because sometimes it depends on the internal architecture, but the PTP packets will get punted. The ping packets, will actually get lost because it'll get punted to the PTP processor, and it won't ping in return. So make sure the loopback addresses are working before you define the PTP, and then try and figure out what's happening. Then the basic thing we're going to configure is an ordinary clock slave, sort of most basic. We have a master out there. We need a slave to sync to the master. And the CLI to do it is PTP clock ordinary. It's an ordinary clock, and the domain, normally there's a domain number. Frequently 0. For other profiles, it may change. For instance, you might find other values there like 4 or 6 or so forth. Then I'll talk about telecom profile in a minute. The most important thing on the 901 is these priority fields, and priority 2 is not as important, even though I've got them both included there. But these priority fields are sent from the master to the slave, and what it basically does is try and indicate the priority of a particular set of masters. Now, the way that the ASR 901 works is that when it first comes up, it comes up in what's called master mode, and it will, if it sees a master out there, it will say, okay, now I can become slave to this master. Now, for that to happen, it has to see a master out there that has a higher priority. Now, a higher priority means a lower priority 1 value. So priority 1 here, 200, is higher than the standard default. The default is 128. Now, the problem is that the default on the Grandmaster will be 128. The default on the 901 will be 128. So if you don't change this priority 1 field on the Grandmaster and make it lower than 128, or you don't change it here on the slave to make it higher than 128, it will never go into slave and start transferring packets. So it's particularly bad on the 901 to do this. So if you have a 901 and you've configured it and nothing seems to be working, go and have a look at the priority 1 field on this device and also on the Grandmaster. A trap for young players, and I've fallen into it myself as well. So priority 1, on every page I will put priority 1 200 on the slaves and 100 on the masters to make sure this doesn't happen. Then we define the clock port. In this case, we're defining a clock port. We just give it a name, and it is a slave. So we are ordinary slave. We've got an ordinary clock slave port being defined. And then we define the transport. The transport is IPv4. We'll talk about Ethernet later, but mostly it's IPv4. It's unicast. And then we put the name of the loopback interface, which is this one here, that we are going to use for PTP processing. And then we set negotiation. And negotiation will then have the slave negotiate with the master things like packet rates. And then we define the clock source, and the clock source is the IP address of the master. And then what it will do, once you click return on that, it will then start communicating with the master. It will then synchronize with the master. That may take some time. It may take 30 minutes by the time it gets enough packets to be able to synchronize, and that's completely normal. And once it's synchronized, what you then, well, you don't have to wait, but once it's synchronized, you can synchronize the internal oscillator to use the PTP as input. And the way that this is done is network clock input source, and the special device you're using is top standing for timing over packet. It's basically the pseudo device that's used to say we need to use PTP as the internal oscillator. Now, this is not the time of day. We'll talk about that in a minute. This is purely the frequency of the internal oscillator in the platform, the T0. And this is like defining clock source line, or on normally on a platform is that you're saying the internal oscillator will be synced to it. Another thing to point out, the 901's very good about this, is that you can mix clock inputs. So you can have PTP as your primary source, and then you can have gigabit Ethernet 1, for instance, as a backup. Normally you do it the other way around, because physical distribution of frequency is better than packet-based, just about always. But you can, for instance, if you had it the other way around, priority 10 was gigabit Ethernet 01, and priority 20 was top 012. That would mean if you ever lost your SyncE, you could use PTP as a backup. Of course, normally if you're out on a cell site, then you might only have a single interface. So if you lost your gigabit, you might have lost your PTP as well. So you can mix them. You can have both TDM and packet-based backing each other up as frequency input. I won't touch on this too much, but according to 1588, PTP carries clock quality in data sets, and there are various data sets. So what happens then? The Grandmaster has a set of data. It's called a default data set, and it sends its data down to the slaves, and the slaves keep, when they receive that, they call it the parent data set. And so when a slave receives announce information from the master, it gets this data and it keeps it in these data sets. So you can actually go and look at them, and I'll just sort of put them there. That there's default data set, and then there's a parent data set which you inherit from the master. So we might cover that a bit more. We're thinking of doing a troubleshooting section where we would cover this a lot more. But what this means, of course, is that if your T0 has been driven by your clock from the PTP slave, like you've used clock source TOP 012, then what that means is the PTP parent data set which you've received from the Grandmaster is the quality of what your internal clock is. And so if you're synced to a PTP master, which is primary reference clock, then you will show as being synced to a primary reference clock. And the way that it does this is that PTP has to take its clock quality information, which is usually in the clock class field, and it will turn it into QL levels from G781. Now, I talked about this at the end of part 1, but this is really where it comes available. So the NetSync process, which is the thing defined, the 781 process, which is calculating the automatic select the best clock mechanism. To use PTP and to figure out how good a clock quality is, it has to convert this clock class field from PTP into a G781 value. And normally that's done when we configure the telecom profile on the 901. So this is specifically the 901, which is most case here. For the 903 and the 24CX, they both support 2 sets of clock translation, so it's not as important. But for the 901, it's almost always need to configure telecom profile, and if you don't get what you want, then try turning it off and see how you go. This just gives you a look at the way this works. As I say, there's 2 mechanisms of doing it. One is this alternate best master clock algorithm from telecom profile, which is G8265.1, and what that allows it to do is 2 different mechanisms. One with best master clock algorithm is a boundary clock port can change between slave and master under BMCA control, and that still works if you don't have telecom profile enabled. But if you have telecom profile enabled, then this is where you get this alternate BMCA, which is what we're normally using here. I just put an announce package in there just to show you the sort of information that gets transmitted backwards and forwards. So I won't cover that too much. It's a slightly complex area, the difference between the best master clock and alternate best master clock. So you can do more reading on it if you want. But here you see the sort of information that's set in these data sets, and gives you a look at the sort of information. You notice the priority 1 field. As I said, it's a default there of 128, and the clock class is saying this is a master clock. So as I said, there's 2 methods of mapping clock class. There's the telecom profile, which is the one that we mostly use. That's why I recommended turning it on. And there's the default method. So really the takeaway from this is that normally you want to turn on telecom profile. I did say before about the domain value. Domain values are normally 0. People don't bother setting a domain value, but if you do have telecom profile, then to be compliant you need to set the domain value between 4 and 23. So I'll sort of leave that in there, mainly for reference if people come across it, rather than try and explain it now. The other thing the 901 supports is the ability to work in a very high jitter network. If you're running over a network has a very high PDV, which exceeds the standard profiles which it's been designed around, then you'll have problems trying to sync. And to do that is it can be very difficult. Like if you use microwave and stuff, you can get very high jitter. So there's a special mode called servo mode high jitter, and then it will be a lot more. It will allow a lot wider variance in PDV and still be able to sync. It won't work really for phase synchronization, but it will work for where you need frequency. It might take longer to lock, but if this is your only option, then it is worth turning on high jitter mode and seeing if you can get your frequency sync to run over an extremely high jitter network. As I said, typical way is like microwave links. Configuration for the 903, a little bit similar. I'll just point out the differences really from the 901. Again, we define a loopback address. Again, you want to be sure of the priority. It's not quite the same as the 901, but in general, you do want to be sure that the priority is higher than the master. We configure a slave port. And what you can do here is you can configure clock source, and you can configure backup clock sources as well. So here we have a clock source 0, which is our highest priority PTP master. That's another PTP master. That's another one, and so that it gives you the redundancy you require. I should also point out here, if you need telecom profile, then you can put the word telecom profile on the end of this. On this end of this slave. So slave can support telecom profile, as we said in part 2, and master, but not boundary clock. We can also define timeout, like the number of announce messages, which is the message I just showed you, which is coming from the master announcing its clock quality and so forth. You can actually define the number of announce messages you can miss before you declare the master is no longer reachable. Similarly, we can set network clock to take our T0 and to drive our internal oscillator. So we say PTB domain number, which is whatever this domain number is up here, which you've defined as typically 0. Difference in the 901, you cannot define these together. You cannot say I'll use PTP to drive my clock and I'll have a backup source of gigabit Ethernet or TDM. Once you've defined PTP, you can only have PTP as a single source. We'll see a little bit later, that's not a huge problem. The 24CX, only because PTP doesn't run on the other two, but similarly, you define a loopback address. It's very much the same as the 903. In earlier versions, you didn't have to define PTP as an input to your system clock, because there was only it assumed as soon as you configured it that PTP was going to be your input. But from 14.5.3, which was released in July, then you have to define it as well. Network clock input source, I want it from PTP. So now we talk about, we have PTP, we have a slave, and we now have available to us frequency to output. We've already covered a lot of ways of putting frequency out with SyncE and TDM and so forth. Now we're going to talk about some of the other specialist interfaces, like 1 pulse per second and time of day. So this is how we've got phase, we've recovered phase, and we're now going to distribute it to downstream systems. So here we have the 901. We have a slave defined. We are taking input from our TOP 0/12 device. If you want to output TDM, SyncE and bits, well, we've showed you how to do that in the previous section. TDM, you clock source internal, although in the 901 that's the default, so you don't have to do anything. SyncE, you just define synchronous mode, and then it will negotiate to be the master. Bits output, we showed you how to do it with the output source command. Now we are looking at outputting phase. So in this case, we go to our PTP clock definition, and under that we define our time of day output. And really this is fixed, this is just the time of day port on the front of the machine. Now it's a slave, so it is going to put time of day out. When you're a slave, you give it out. When you're a master, you take it in. So there's no real configuration there. It's one way only. The format of time of day, there are options I cover, I think, on the next slide. 1 pulse per second out. You can play around with some of these things. You can put offsets for 1 pulse per second to take account of delays. You can define pulse widths and so forth. A lot of people wouldn't play around with those, but it is available to you. What we're also able to do is we're able to output 10 megahertz signal. So if you want to output a 10 meg signal. But one slight difference here is the 901, you cannot update the system clock from PTP. I don't know if they're going to change that or why that is, but I know that certainly the recent versions it doesn't work. So if you want to have the system clock updated, you probably have to run NTP over the top to make sure the system clock's up to date. So that's, the phase is still there, the time of day is still there, but you just can't update the system clock. 903, again pretty similar. You have time of day. In this case you have two, because on the 903 you have two route switch processors. The 902 you only have one, because it's a single route switch processor. And similarly you define the output of the text. Equivalent on the 1 pulse per second, again there's an R0 or a 1 to output the 1 pulse per second. 10 megahertz, you can put the output on the 10 megahertz. There's actually you can output 10 megahertz by putting 10M. You can actually output 2 megahertz on that same port by putting 2M. So if you put external R0 2048, it goes out the bits port. If you put 2M, it goes out the 10 megahertz port, and if you put 10M, it goes out the 10 megahertz port. And you can update the time of day clock from the PTP on the 903. I'll just cover for a few minutes redundancy. The 903, as I said, is a redundant platform, has two RSPs in it, unlike the 902, the 24 and the 901. So ESMC and SSM, it says SSO coexistent, not SSO compliant, so that means they know about each other, but during switchover the router will go into holdover mode, and then it'll restart the clock selection when the switchover completes. So as a changeover happens, it will then come back, the clock selection will restart, and then it'll sync to the new source. The interfaces on the 903 all support the use of a Y cable. So you can have a bits or a 1 pulse per second 10 meg time of day come in and have a Y cable. which will be simultaneously connected to both the active and the standby RSP. And if you do that, you need to configure the Y cable. You say platform network clock Y cable. And what happens is when you turn on the Y cable, that means all the outgoing signals are only ever driven by the active processor. The standby processor squelches its output. And then what happens is if it switches over, then it switches over so that the standby becomes active, and then the active, we'll say it crashed and comes up as a standby. It will not produce the output. The output will get switched on the active processor, which took over. In the in direction, the signal is recovered by the active processor, and the other one just ignores the signals. They are visible, especially the bits is visible to the other one, but they don't act on it. And when it switches over, the new route processor will start recovering the signal from the ports, and the standby will ignore them. So when you have a Y cable, generally you would configure the bits input here. Now they would obviously be the same because like it's the same signal coming in. So you would have one configured on R0 and one configured on R1 for bits input. The slight interesting piece about bits is actually behind the faceplate there is actually an internal Y cable as well. So even though you don't have a Y cable on bits, there is actually an internal Y cable. I think I have a slide on that next. Unlike bits for 10 megahertz, you really need the Y cable. So there's no internal Y cable here. If you need 10 megahertz, then you want redundancy. You need a Y cable, and you need to configure it on both interfaces. If you do 1 pulse per second and 1 time of day, it just assumes that you're doing it on both of them. So when the other one comes up, it will actually start putting out the signal on the active or receiving it on the active. So if you're a master, receives. If you're a slave, it sends. As we say here, the two sources of a Y cable are almost optional for bits because you have this internal Y cable, and the sets can see both bits input. So even if you have an active standby without a bits connection, it can see the bits on the standby. Obviously the standby has to be up for that to work, so otherwise you're in problems. So really to get full redundancy you need a Y cable for bits, but if you don't have it, it will actually still work, unless the actual standby processor is down. Now, talking PTP slave, the ME3600X, 3800X don't support PTP, so this is for the 24CX only. Absolutely similar to the 903. Of course, the time of day clock is just TOD00, output 1 pulse per second. So fairly straightforward. It'll put out the time of day in those formats. You can also output the 110 megahertz. It's called external 100, 10 meg, and it will output it. You can also, on this platform, update the time of day clock. Time of day formats, many formats available. We support the first 4, NTP, Cisco, NEMA, which I explained I think on the first session, and UBX. Hybrid slave, all the platforms support hybrid slave. The difference here really, it's very much the same as slave. The only slight difference is you use a TDM source, SyncE most likely, as a frequency source, and the PTP will use PTP stack for phase and time information, but it will not use the PTP for frequency. This gives you, we explained in part 2, gives you a lot better result because the frequency source comes over a physical wire, and it's usually a lot better than a packet-based frequency recovery. So really the only difference here from an ordinary slave is to put the keyword hybrid here, and this means that it's now going to accept the CLI to define a SyncE as a frequency input. So again, all the same things as before. We define a loopback address. We have the priority wants to be greater than the master. We still define a slave. The only word is the addition of the word hybrid. And what we have to do is to define an input. So we need to say we need to take a frequency input from somewhere. So because we're not using PTP as a frequency input, we can define a synchronous Ethernet. So as we defined on the SyncE input section, then it's the same as just taking SyncE in. So the hybrid means take the frequency from the gigabit Ethernet, take the phase from PTP, and you'll get a much better solution. Of course, as we say, you can't take the timing over packet as a network clock. You really need a valid physical interface, and normally it's SyncE. 903 also supports it, again exactly the same, hybrid. You have a clock source, you can have multiple clock sources similarly. So hybrid slave, very much the same as slave, only the addition of the keyword hybrid and the ability to define a synchronous Ethernet input. So the way you do that, a 903 interface synchronous mode, and then you define the network clock input source interface 010 in this case. I say this is exactly the same as just doing a synchronous Ethernet input. So a couple of points to make. If the PTP session fails, the system will remain in frequency lock. So even though you lose phase, you'll still see frequency lock because you still have the gigabit Ethernet connected. But if the frequency fails, if this goes away, PTP will not be used to recover frequency. So it's really much better to have a redundant frequency source, like having 2 gigabit Ethernets, because that will give you redundancy. If you lose PTP, but you still have the frequency sources, the way that it works is that the frequency source stability you're getting from Synchronous Ethernet is so good that it will actually keep phase fairly well aligned for a long period of time. So it's actually not a huge issue to have redundancy with PTP. As I said there, you can actually, on hybrid mode, you can only use a single PTP source. So sorry that I'm the previous slide. There is a difference there. You can only use a single PTP source in hybrid mode, but it's not really a big issue because it's more important to have redundancy at the synchronous Ethernet layer. So you define 2 priorities, priority 10, priority 20, 2 gigabit Ethernet interfaces, and then if you lose your PTP, you'll still have very good phase accuracy because your frequency synchronization will be keeping your phase aligned. .24CX, very much the same as the 903. It supports it as of 15.4.2, which I think was January, February this year, 2014. Again, you can only have a single clock source in hybrid mode. So you can also support in a hybrid slave. There's telecom profile is supported because it's a slave. Not supported in boundary clock, but supported in slave and master, even hybrid. Hybrid slave, of course, because you're hybrid, you now need to define a SyncE input. Again, you can go back to the section on SyncE. It's exactly the same. And then you just define synchronous Ethernet as a T0 source. Same provisos as before. If the session fails, it will remain in frequency lock. It'll be a very good frequency lock, of course, because of its physical frequency inputs. The phase will be also very good holdover, but PTP will not be used to recover frequency. So, the fact you only have a single PTP clock source is not as important as having the redundant frequency sources. And so that's configuring slave clocks. So now we can move on to moving to PTP master clocks. So with our nodes now being PTP master clocks, we need to have a source of frequency, a source of phase, and a source of time to distribute to our downstream nodes. Now, of course, we've investigated how we do frequency in previous sessions, in previous sections here. Now we're looking at how to get time and phase inputs and frequency inputs into the PTP master. Now we talked about frequency before with bits and TDM and so forth. Mainly here we're concentrating on getting the time and phase inputs. So the way that we do that is through the physical plugs on the front of the device. We need some sort of physical input that we can put them in, and here you see them for the various platforms. So looking at the ISR 901, we have a time of day platform, time of day port, sorry. We have a 10 megahertz for like GPS, and we have a 1 pulse per second for phase. Also on the other platforms we have 1 pulse per second inputs and outputs, and you can see on the 903 for instance, the 1 pulse per second input and out. The 901 economizes a little bit for space on the front faceplate. It has plugs that are dual purpose, so both input and output are on the one pulse per second. The other ones are separate. The 901 takes advantage of the fact that if you're a master, you're taking time in. If you're a slave, you're putting it out. So it turns the direction to transmit or receive based on whether it's configured as a master or a slave. Whereas the other devices have a little bit more flexibility in that you can have different plugs, and depending on what the platform is running, you have it connected to different devices. So we've already looked at TDM and SyncE and bits being input to our internal frequency, our T0. So we have our local frequency as a reference for PTP, so that's all sorted out. Now what we have to look at is getting our physical time and phase inputs. Firstly, I should just say, when you're got a 901 with a master license, master clock is included in the IP base license, so you don't need a separate license for ISR 901 master clock. It's included in the IP base license. If you run a boundary clock, then you need to install the advanced timing license. This is not true for the other platforms. For the other platforms, a boundary clock and a master clock are both, if you like, lumped together, and there's a timing license to support boundary and master clock. So slave is included in the IP license, but master and boundary isn't. The 901 master is also included in the base license. The 901 supports, being a more modest platform, supports 36 slaves in unicast negotiation mode, which is for this platform more efficient. 19 if they're statically defined. So unicast negotiation is normally the way you want to go, where the slave negotiates with the master. So we know now we need time and phase input. We have seen the plugs on the front of the platform, so we need to define it. So where we go into our configuration mode, we go into our PTP clock configuration mode, and then we define a time of day, which is that's the device, and then we define the format of the time of day as being input. So it could be like NMEA, if it's like a GPS device might output NMEA sentences, but it could be Cisco or NTP if something is providing a particular time of day. Similarly for the 1 pulse per second, 1 pulse per second input, so that's all pretty straightforward. And then the PTP master servo on the ISR 901 then can start negotiating with slaves and sending packets out. However, if you don't have phase and time standards available, references available on the platform, then the interfaces will go down, and PTP will realize that, and PTP will adjust its clock quality, and it will send it down in its announce messages. It will change the clock quality and send to the slaves and basically say that it's lost its PRTC, its reference time clock. So I've showed you a couple of slides back the announce message, and you saw in there where there's a clock class value. Well, the clock class value will change. All the mapping between clock class values and G781 and so forth and SyncE I put at the end of part 1 of these series, so you can go back and check. So 104 is very quickly will let the downstream systems know that it has lost its references. And this is how really you can ensure that the downstream slaves can be configured to go to backup masters, and then they will they will then keep synchronization, because they will fail over to a different master. So what's happening here is if the 901 is the OC master, so the external reference is providing input to the T0 clock. The T0 clock is used by the OC master, the ordinary clock master, to populate these clock class values. So the system takes frequency and time and inputs, and then it defines, we've seen before how you define those inputs, and it will go through the NetSync process G781, and it will say, okay, my T0 is coming, frequency is coming from, say, SyncE, or it's coming from my bits port. That information will be used by the master to populate these data fields, which I showed in the default data set, particularly the clock class field. And for that to happen, we touched on it a bit when it was talking about slave, but G781 quality level needs to be mapped to a clock class value. And this translation and normally can be done several ways. On the ASR 901, really the way it's done is according to the telecom profile G8265.1, and it populates the default data set, which is then sent to the slaves and becomes the parent data set. It's sort of for this reason, for this mapping, that the 901 most normally needs to be configured with telecom profile. It's just about 95% of the scenarios I've seen of the 901 being used telecom profile for both slave and for master is configured with telecom profile. But if it's not doing what you want, then perhaps you might try it without it. But it's really about this translation is the most important factor. ASR 903, you'll see some similarities here with confining the slave, and also with defining the outputs. We're just defining a different direction, but sort of we've cut this presentation into nice little chunks, so that if you're interested in PTP inputs, then you come here, and outputs at the other place. So we're sort of repeating it a little bit to keep it formally structured. So we said we got our TDM SyncE and bits inputs to T0, so that's all defined. On the 903, I said we need a clocking license for boundary clock and master clock, so you do need a license to run it as master. It supports up to 64 slaves, and we're looking at 128, but it's certainly been done for 64. And of course, as we've seen, we need phase and time inputs, so we need one pulse per second, and time of day inputs. Similarly to the 901, we just define the PTP clock as ordinary clock. We have an input R0 and R1. Remember, R0 for the 903, first RSP. If it has two RSPs, it can also have a R1. The 902 only has a single RSP without redundancy, so it's R0. But the 903, you have redundancy. The time of day, similarly, R0 or R1 the input, and then the format. Typically, similarly, the 901. Again, the formats we support, you saw on the time and phase output section for Cisco, NMEA, NTP, and UBX. What's a little bit different in that the 903 also supports the ability to set the time of day for the system from the GPS port, so it can actually read this time of day input port and use it to update the time of day clock on the system. So we've seen how the 903 can also set the time of day coming over PTP, but it can actually set it directly from the device externally that's providing its reference for PTP. For information about redundancy, we said there's two RSPs available on the 903, so there is the ability to have redundancy for the output signals, or similarly the input signals. And in the PTP slave area where we talked about physical outputs, we talked about redundancy and Y cables and what happens when you get failover between RSPs and so forth. So if you're interested in input redundancy, then go and see the slave section for the 903, and there's a couple of sections and explanation on that there. 2400, 24CX, I keep calling it 2400, 24CX. We're only talking about here the 3600X, 3800X don't support PTP, so it's the 24CX. Similarly to before, we have the local oscillator is getting a frequency reference, and the local oscillator then is used to drive PTP. We have 64 slaves supported using 32 and 16 per second delay request packets. Similarly, this 24CX requires a license to support master and boundary clock. TDM SyncE and bits input, we've seen how we do that in the previous sections, and now we're getting the inputs for phase and time. Similarly to the 903 and the 901, PTP clock ordinary, the domain number, whatever it is, and we input 1 pulse per second, we input time of day. Same formats as before, and the time of day clock input source, again we can set the system time with the GPS inputs like the 903. So except for the name of the device, it's the name of the port, it's pretty much exactly the same. We talked in part 2 about 1-step and 2-step, and here we see a 1-step clock on the left and a 2-step on the right. 1-step clocks are where you send out a sync packet and you put the timestamp that the packet was sent in the packet itself, the T1. In a 2-step, you send out the sync packet and don't worry about trying to timestamp it, and then you send a follow-up message which contains the value T1. A lot of master clocks are 2-step for various engineering reasons. One of the negatives of the 2-step is that you're actually generating a lot more sync traffic from the master to the slave, which mightn't be a problem for 30 or 60 client slaves, but big grandmasters can support thousands of slaves, so obviously doubling the traffic can be a significant hurdle to its scalability. So there is some advantages to 2-step, but certainly there are some advantages to 1-step. You'll see that some of the telecom providers are starting to favor 1-step really because of traffic generation and out towards the edge, and also the load on the grandmasters. So just explaining here, the masters from our portfolio here are 1-step, but of course our slaves have to interact with our 1-step or our 2-step masters, so you have to do that, and of course we do. SPAG, if you don't remember, is our service provider access business unit, which products you're seeing here. Now, as part of the configuration as well, you are allowed to on the slaves. We didn't talk about it too much because there's not too much you can configure on the slave, but you can configure some things, and you can also negotiate between the slave and the master things like packet rates and some timeout intervals. On the slave, we are able to configure the packets that are generated on the slave, and on the master the ones that are generated on the master. So these are defined somewhat confusingly using log base 2 values of interval. So it starts, if you start at 0, so if you define the interval to be 0, it means 2 to the 0 or 1 packet every second. And numbers larger than 0 means 1 packet every so many seconds. So 8 seconds is 2 to the 3, so 8 seconds between packets. Less than 0 in negative numbers means fractions of a second. So down the bottom there, -7. Yeah, it's basically 2 to the -7 means 1/28th of a second, which means you're going to send 128 packets per second. So looking at the packet types, announced, sent from the master, you define how often you want to send those. Normally the defaults are okay on certainly on announced. Sync, sent from the master to the slave. The delay request is sent from the slave to the master, and then it responds with a delay response. Obviously you have to take account of all that with your load on the master when you're sizing how many slaves you want on the master. The packet rate is directly can affect the number of slaves you can support. Of course, the higher the packet rate, the faster it'll lock on, and the better your solution for for clocking, the better your timing solution. So it's a bit of a trade-off there. Timeouts can be configured on the slave. The most common is the announce timeout. And what the announce timeout says is how many times you listen for what interval of announce time you listen for and don't hear one. So if the announce packet is sent once a second and for 4 seconds you don't hear from an announce, then you know, or you assume, that your master is gone, and you then go around looking for another master. And the normal default for this value is 3. The default for announce packets being sent by the master is usually 0 or 1 packet a second. Again, that's normally fine. So now we've got our inputs to our master clock. Now we need to define our master clock. So the first thing we do is we define a local loopback address like we did before. I didn't explain before, but the loopback address, this is loopback 1589, but normally on the slave definitions I said loopback 1588. There's no reason for that number. It's just purely convention that people say, oh, loopback 1588's been used for PTP, and I know that's I know what it's for, so it's not a routing loopback address, and you treat it appropriately. In this case, I've made this 1589. If you're only running a master, you could use 1588 as well, but I leave it 1588 and 1589 in case I want to run boundary clock where I need 2 loopback addresses. So I have the slave as 1588 and the master is 1589. But that's just convention and convenient number. You define an IP address. Okay, we ping it before we define PTP on it to make sure that the ping packets don't get punted to a sets device or something that it can't respond. And then similarly to the slave, we define a PTP clock. It's an ordinary clock. It's an ordinary master this time, not an ordinary slave, but and the domain number that we want. In this case, a 901 PTP telecom profile. Now, priority here, you'll notice, is a difference. Remember, we said before that the standard default priority is 128, and that if you configure a master or a slave, it'll come up as 128. But we also said if you're on the 901 and the slave is 128, and you want it to be a slave and it's 128 and the master is 128, it will never become a slave. So you really must have, especially on the 901, but on other platforms as well, you really must ensure that the priority of your masters is a lower value. Higher priority is a lower value. So what you do is on the masters, I always set the priority 1. Priority 2 is not as important, but certainly priority 1 has to be set lower than 128. And on the slave, I always set it higher than 128. And no matter what I install, what I configure, I always do that, and then you don't get into trouble. As I said, I've been bitten by the 901 with this problem a couple of times, so I'll never make the mistake again. There's also other platforms that I've seen same issue. So make sure you configure a master priority less than 128 and on the slave more than 128. We configure a clock port. We just give it a name. It's called MyTP master, and instead of slave we use the keyword master. So now we're defining the master side, not the slave side. Similarly, it's IPv4 unicast transport. Our interface is the same number here that we used up here. So it could be 1588. I've used 1589. Normally you want negotiation, so that you negotiate with the slaves. Otherwise you have to specify each IP address of a slave, but normally you get negotiation, and that means the slave's asked to connect to the master, and then it allows them to be a slave. These are the values that I said you can configure. Sync interval, normally it's -6 or 64 packets a second. Normally with a angle bracket is 0 or 1 packet a second. ASR 903, remember for this you need a license, boundary master clock license. A special timing license. You didn't need the timing license on the 901 for master, only for boundary. We define again a loopback address 1589, very much the same as before, where it's an ordinary clock. We set priority to be 100. It's a master interface. It's IPv4 unicast. This is the loopback address, which is the same as the one up here. Negotiation define if you want, sync and announce intervals changed, and you're done. So that's pretty straightforward. 2400CX, again, you need the master boundary clock license. Also remember, this isn't supported on the ME363800 because they don't support PDP. I define a loopback address 1589. Again, priority less than 100. It's an ordinary clock. It's a master clock. It's a unicast. It uses the same loopback address like it did up here. Negotiation, what you want. You can define these parameters if you want. So as you see, this is very much like the slave, like all the other ones. It's once you've got the basic pattern down, it's all pretty straightforward. And that is how to configure master clocks. So we've seen there that besides configuring master clock, we've also seen how we're going to configure inputs for the PTP master. Previously we saw slaves and how to configure outputs from slaves. So now what we're going to do is have a look at boundary clocks. Now if we remember when back to part 2, we have ordinary master clocks and we have ordinary slave clocks. We've already seen this piece here where we have reference inputs to an ordinary master. We start a PTP stream. We've already seen how we do an ordinary slave. We've seen how we do our outputs from PTP, from SyncE, and also our 1 pulse per second and time of day. And now what we're doing is we're going to look at a boundary clock, which is a node that sits in the middle. Its function, we covered in part 2, is to clean up noise in the packet stream, and it's also to take out node delays or try and mitigate the effect of variable node delays and packet delay variations through particular devices. A boundary clock is a node that consists of 2 ports. It has a slave port and a master port. The slave is a slave to the master, this master, and the master to a downstream slave. So what we're going to do now is we're going to look at defining a boundary clock. So on the 901 here we need the advanced timing license so to enable boundary clock functionality. So the CLI probably won't be there unless you define it. So we're defining loopback addresses now. We need to define 2. We need one for the slave port, one for the master port. As said before, loopback 1588 for one, loopback 1589 for the other, which is why our master ports had 1589. It's very similar to what we did before. So PTP clock boundary domain, and this then shows what our domain number is. Then we define the slave clock. So my PTP slave, we just give it a name slave. Similarly before, IP for unicast, our interface number, which is like one of these loopback addresses, negotiation, which is what you want, and then the clock source of the upstream master. And then we also define another clock port. This one's called my PTP master. We use the keyword master here instead of slave to say that this is the master. Again, IPv4 unicast. Again, negotiation. And we use the different loopback address. We use this one up here. So now we're running as a boundary clock. The only difference really is this keyword boundary. Okay. So normally we had ordinary clock in there. We had ordinary and we had slave, ordinary and we had master. Now we have boundary, and you can have both a slave and a master. So that's, again, it's just an extension of what we had before and change one keyword. Similarly for the 903, very much, pretty much exactly the same. You need to install the master boundary clock license. We define the 2 loopback addresses, 1588 and 1589. And then we configure PTP clock. Again, it's not ordinary, it's boundary clock. And our domain, our priority for a slave, my PTP slave. We configure 1588 as the port for this guy. Negotiation, our clock source. And then we configure a master. 1589 is the other loopback address. Negotiation. Again, then you have boundary clock running. What I've also showed too is that if you're running boundary clock, you are able to output the 1 pulse per second, time of day, and so forth, mostly. There's a couple of little exceptions, but in general, in boundary clock, you're getting your time and phase from the upstream master. They don't assume that you can input it halfway down the chain. So generally, when you're a boundary clock, you can output, you don't input. So this is to output, is you use this keyword here, output 1 pulse per second, exactly like we did before. We can also output the 10 megahertz signal. We talked about that before. I don't think I actually had it in the slide, but you externalize 10 meg, that puts the 10 megahertz out a port. You can also put a 2 megahertz out the GPS port by putting a 2M there as well. We can also, like we can as a slave, we can update the system time on a boundary clock. It's like we could do on the slave. We couldn't do this on the 901, but we can do it on the 903. The only slight tickler is that the time of day output is not supported in boundary clock mode. So you can output 1 pulse per second, but you can't output time of day. It's currently blocked by software, although the hardware is capable. Now, to be honest, I haven't checked that in the latest release or two. I've been through this presentation and I've personally checked like 90% of this CLI, so I know it works. Maybe 95. Sometimes it wasn't available, or I couldn't get a machine in time, or it was running the wrong version. But so I can put my hand on my heart to say I haven't tested it recently, but certainly that used to be the case. So don't assume that on the 903 time of day output will work in boundary clock. It'll work in slave, but not in boundary clock. Again, boundary clock on the 24CX, we need the license, we need the 2 loopback addresses like we had before. We need the priority. We need to define a boundary clock, not an ordinary clock. We configure a slave port using 1588 loopback. We configure a master, configuring loopback 88. Again, there was a issue with some of the earlier versions which you didn't use to need PTP to drive the local clock, but that's not relevant anymore. So PTP clock import source. So if you need to have PTP drive the local device, then you configure this much like you did with the slave clock. So you can use this to do it, and you also can do the same thing on the 901, the 903. Exactly like as if you're a slave. But I just put this note in here before because earlier versions you mightn't be able to do this, and I thought I would remind people before 12.4.3, which was July 2014, you didn't have to configure the input source, but now you do, like the rest of the devices. It brought it in line with the rest of the devices. So that's it's boundary clocks. Now, when we did slave clocks, we introduced this concept of hybrid slaves, where you take the slave phase time of day from PTP and you take the frequency for TDM or SyncE, and the same thing happens with boundary clocks. So you'll see it's more of a combination of hybrid slave and just adding boundary clock to the equation. So the 901, again, you need to install the timing license. As we said, for hybrid mode, it's best if frequency or phase are traceable to the same master. For like boundary clock, we need 2 loopback addresses, 1588, 1589. We need to configure then a boundary clock. So we configure PTP clock, it's a boundary clock, not an ordinary clock. Like we did with the ordinary clock, we just put the word hybrid on the end of it, which indicates to PTP servo that it's going to take frequency from an external source that's not PTP. Priority is configured, then we configure a slave side of the boundary clock. We use the loopback address, negotiation, the clock source for the master. And then we configure the boundary clock master side. Same thing, we just use the master keyword. We use the other loopback address. Okay, and then what we have to do is we have to define a frequency input. So we take, in this case, this might be synchronous Ethernet. So you see this previous section on synchronous Ethernet input. You go and look at how to do that there if you're not sure. But you define synchronous Ethernet on the interface and then you add it to the input source. So hybrid means it will take its frequency from this interface and it will take time and time of day and phase from PTP. As I said, you can't cheat. You can't put the timing over packet as a network clock. So it's the same restriction on so if you're doing that, it's not a hybrid clock anymore. It's actually it's just an ordinary slave clock. A hybrid clock, you need a physical clock source. It's an advantage, it's not a restriction. So in the interest of time, which seems to be slipping away from me, you'll see the again, a repetition. This hybrid mode is exactly the same as hybrid slave from the 903, very similar to the 901. Typical boundary clock, we add 2 loopback addresses. We define a boundary clock. We add the keyword hybrid to the end of it to indicate that we are now going to take our frequency from a physical distribution source, not a packet. We define the boundary clock's master side of it. We use the other loopback address, and then we define another Ethernet interface for frequency. And so in this case, I've just taken one interface on a RJ45 interface module. You turn on synchronous mode, and then you define that synchronous mode to be an input source for your T0 for your internal oscillator, so that NetSync can use it to select as a physical source. Now, a couple of things to note about this too. If the PTP session fails, so if your PTP just stops sending packets, it will remain frequency locked. So you don't lose the sync. There is one slight restriction with hybrid mode, same as with slave, is that you can only have a single PTP clock source. So you can have multiple frequency sources, but you can only have a single PTP. You can't have multiple masters when in hybrid mode. As I explained for slave hybrid mode, it's not a huge issue because the frequency source is so stable for things like SyncE that it basically keeps the phase aligned for you. One way I like to explain this is like cars driving down the road. If when it says like there's fog or sand or something on the dust on the road you can't see, they'll say keep a greater distance from the car in front. Well, if you think of phase really is your distance from your car in front, so what you're doing is if you lose your phase and frequency sync, you don't know how fast you're going, you don't know how far the car is in front. So you're sort of relying on your speedometer to say, well, I think I'm still doing 100 kilometers an hour and I think the guy in front is. So what happens with hybrid mode though is even though you don't have a phase offset, so you don't know how far you are from the car in front, so you don't know if you're 100 meters or 300 meters, but if when you lost the ability to measure how far away you were from the car in front and you're 100 meters, and then from that point on you're both doing exactly 100 kilometers an hour, then you will still be 100 meters away. It's sort of a bit of a long-winded analogy, but if you think about it, really phase is telling you how far apart the cars are and frequency is telling you how fast you're going. So if you know the car in front's doing 100 and you're doing 100 and you very accurately can measure you're doing 100, then you will not gain on the car in front and you will not fall back. So that's a good way to sort of understand what's happening here. So if you have a single PTP source and you lose it, it's not a great drama because you have a very stable frequency source, so it can keep the phase aligned. Another point to note is that if you do lose frequency input, your reference, your gigabit Ethernet, then PTP will not use frequency, will not recover frequency with PTP. So you'll lose your frequency source. So The takeaway from this is it's more important to have backup for your frequency source, so to have two gigabit Ethernet ports providing SyncE and a ring, than it is to have two PTP masters. For the 24CX, as of 15.4.2, which I think was like a January, February, it also supports hybrid. Again, same restrictions and suggestions from the 901, the 903. Best if you can trace frequency and phase to the same master. You need a timing master boundary clock license. We again define two loopback addresses exactly like we did for boundary clock. And then we define hybrid mode. Again, we're doing boundary clock, not ordinary clock, but just like we did with ordinary clock, we add the keyword hybrid. Define the priority, we define the slave port. Again, unicast negotiation 1588. And then we define the master, the PTP master, again using the other port. And then I just sort of cut and paste this just to give an example of then how you define synchronous Ethernet on a 2400. But you can go back to the SyncE section and see in detail how to do this. So we just take this one port, we turn on auto negotiation, it's an SFP, and then we turn on synchronous mode. So that starts SyncE running as long as you've got ESMC and everything going. As I said, see the SyncE section. Then we define SyncE to give us a frequency reference. Said it's best if you have two. The same provisos go as the previous couple of slides on the 903. PTP will not be used to recover frequency if it fails, if frequency reference fails, so it's good to have backup frequency. And also, as I explained on the 903 with my car analogy, it's best that you will get a good result even if you lose PTP, as long as you have a very stable frequency source. So that was boundary clock, hybrid boundary clocks. I did put a couple of slides here in on Ethernet transport because it's now supported on a couple of these platforms, which I gave in the overview of support. I'll just sort of put this in here. I won't explain too much about it because mainly we've been talking about IP transport till now, but just so you know that like on a lot of our industrial switches in Cisco, and other platforms, there is support for PTP over Ethernet. Now, starting with the 901, support for PTP over Ethernet is in multicast, and it doesn't use loopback addresses, right? Because it's a layer 2 thing. You don't really have that. So what it does is it uses the interface and it uses MAC addresses. So when you define a slave on an ASR 901, again, it's just an ordinary slave. So no difference there. You're defining, give it a name, your PTP slave, and you're defining the transport. Instead of the transport being IPv4 unicast, it's now Ethernet multicast. So that's really where the difference packs in. You're telling it now we're using Ethernet multicast as transport, and of course our interface is no longer like gigabit Ethernet. We might have things like a bridge domain, which is carrying the multicast traffic. On the master, again, it's pretty simple. You're really changing the slave to be a master. You're again using Ethernet multicast and a bridge domain. And then if you're not exactly sure how to define a bridge domain, this is sort of the EVC on the 901. Say for instance it's on gigabit Ethernet 3, then you define a service instance. The traffic might be coming tagged. In this case I've shown it's tagged with a VLAN 100 tag. So what it'll do is any traffic that appears on gigabit Ethernet 3 that has a VLAN tag of 100, it will take it, it'll pop the VLAN 100 tag as the packet comes in, and it'll give it to this device called a bridge domain. And that bridge domain, of course, ID has to relate to this ID here, and then your traffic will be diverted to the PTP engine. This rewrite also on the piece going out symmetric means that it will push a VLAN 1 tag. So what this means is you're connected to a master which is sending you multicast PTP traffic with a VLAN tag of 100. This is how you capture it and push it into the PTP stack. On the 903, it supports PTP over Ethernet, but it's unicast at the moment. There's currently reasons for that, which is basically a customer wish. Similarly to the 901, we don't use loopback addresses, but you've got to use things like MAC addresses and interface definitions. So there is some similarity. You are going to define a slave on the 903. It's an ordinary slave. You define a clock port. Similarly to before, we're going to say we support Ethernet unicast negotiation. So you're saying that it's going to be layer 2. It's not multicast like the 901. And there's negotiation, so you're going to negotiate with the master. And then you have to put a clock source in, but you don't have an IP address anymore. So you actually got a MAC address for the master. That's an example MAC address. And then there's a bridge domain, like we saw before. There's a bridge domain which is defined where that layer 2 traffic is coming in for. And then there's a priority for the clock source if you have multiple clock sources. And then just to show you here, if you have a second slave, you define a second slave. For instance, it might be on a different interface, and it might have a different MAC address. So again, Transport Ethernet unicast, a clock source is a different MAC address to the one before, and it might be on an interface this time. So the traffic, you can define it, either it's been put in a bridge domain or it's coming in gigabit Ethernet, and it's priority 2. So that just gives you some examples of how to configure slave in both bridge domain and interface configuration. Defining a master, in this case I've just given an example here, Ethernet unicast. I've actually put in a clock destination here of a MAC address for a if there's no negotiation. So normally you get negotiation, you don't need to define a clock destination. Same with IP. But otherwise what the slave will do is the slave will contact the source and it will negotiate. But if you don't do that, if you don't have no negotiation, and then you define a bridge domain that you want to talk over and a MAC address or an Ethernet interface. So as I said, I won't go into too much detail for those, but I just sort of included them for people that want to play around with PTP over layer 2. It's not supported on the 24CX. So almost done. PTP transparent clocks. As I said, we support end-to-end transparent clocks on the 902, 903, 24CX, not supported on the 901. What is a transparent clock? We covered this in a little bit in part 1, a lot in part 2. It's the ability of the hardware to understand PTP packets are coming into your platform, timestamp them on the way in, the way out, and to update a field inside the PTP packet which indicates the residence time. It's a correction field which allows the slave to correct for the amount of time that packets spent inside machines on the network. The idea behind that is that you can calculate. I can't think of the right word, but basically you calculate out, or you by using the arithmetic of this correction field, it enables you to negate any delays of where the packet sent was spending inside machines on the network. So it's a good way of being able to take out packet delay variation of intervening nodes. So we support end-to-end. There is another one called peer-to-peer, which I talked about in part 2, which is not really of interest to us. End-to-end transparent clocks. It doesn't matter really whether the packets are in layer 2 or in layer 3 or MPLS. It'll find a PTP packet and it'll timestamp it, so you don't have to worry about that. If it's passing through, it'll timestamp it. So how do we configure that on the 903, the 24CX? So as I said, it doesn't matter, PTP over MPLS. It's got labels around it. It'll find it, stamp it. The sync and delay request packets is adjusted in this correction field. Now I show there below that when you configure this, you can configure the domain number, but actually it ignores it, so it doesn't really matter. Any PTP packet is going to get stamped. But once you configure something as a transparent clock, boundary clock, ordinary clock, everything is disabled. So it's really not participating in the PTP flow at all. All it's doing is understanding what packets look like PTP and stamps them. There's no license required for it, so any license that supports ordinary clock, which is like the base IP sort of license. There's no statistics. You can't really see what it's doing. There is, if I'm thinking about doing a later video on troubleshooting, there is actually some CLI where you can see that it's doing what it said. But basically, there's no PTP statistics because you're not running a PTP stack. You're not involved. It's all been done by the PHY. As I said, on our SPAG products, then they're one-step transparent clocks. There is a thing called a two-step transparent clock, and really what that does is it takes a sync message and turns it into a sync plus a follow-up. So it turns a one-step master into a two-step master by generating an extra packet. But anyway, we don't support that. Can be done at line rate, and the way to turn it on is simply to define PTP clock end-to-end transparent domain and a domain number. As I said, the domain number doesn't matter because it'll stamp anything. And that's how you turn on transparent clock, which is a really good way of negating any sort of PDV for nodes in the network. But as I said, it then takes it out of the equation for any further PTP processing until you turn it off. Summary and conclusion. So I say supported features are almost identical across all platforms. It's taken us a little while to get here. It's a lot of effort to make different platforms with different features and hardware, and to actually all do the same thing with the same CLI, and we've gotten very close. CLI gives us a fine degree of control. I mean, we have seen really just the configuration of it, but there is a hell of a lot more on the management, which I said we're thinking about with a part 4. But you control all the pieces that you need to. It all works pretty well. For sync to work well, you need things. Sync doesn't just happen with one piece. We often get this. You need a lot of pieces working together to work correctly. The hardware's got to be right. You've got to have the right bits of hardware. You've got to have the right expensive pieces of hardware, because cheap clocking is, cheap clocks. We always said that a cheap watch is worth nothing. Well, it's the same with clocking hardware. Things like oscillators, you've got to do all the thermal engineering to make sure that all things stay thermally good. You get the protocol stacks, the servos, the algorithms that are used to run this stuff, and then the software to support it. They all have to work well for synchronization to deliver what you require. The whole idea behind this series is to allow one, well, certainly the last part is to allow one to take any of these platforms and get it working, and to get them working in unison. So if you want a 901 as a slave and a 903 as a master, or some combination, then with this you should be able to get it all working fine. Because this is really a distillation of all the lessons I've learnt in plugging these devices together over the last couple of years. But it's clear that you can't take a piece of paper out and make sure you're going to get what you want. Really, the best way to avoid disappointment, and this is not just Cisco platforms, this is all of them, is to connect all the pieces together, and then you put it in a real world scenario. You test it with, simulated if you like, but real world levels of traffic, and make sure it gives you the result of what you're expecting. Make sure it meets your requirements, and if you're not doing that, then really you run the risk of disappointment down the road, and that's a clocking. That's not a Cisco answer. That's a clocking question. As I said, we're now working on implementing most recent standards. 8275.1. We're certainly working on the engineering of that. There's the standards have been finished now. As we said previously, it's been done. But now there's some engineering challenge around it as too, because there's a few questions about how we implement some things and how does it work, interoperating with 8265.1, and so none of this stuff is easy, and we're certainly working our hardest to get this stuff done. And that is end of part 3, and I'm sorry it took so long. But I thought it was good to go a little bit slower than I intended and to explain it all in detail. So thanks for listening. Thanks for your patience.